Welcome to this lecture on the canal system in sponges. Imagine a bustling city with a perfect continuous plumbing system, but no moving parts. Today, we will explore how sponges, despite having no organs, use fluid dynamics to survive, feed, and breathe at the bottom of the ocean. Let us dive in. Welcome to our first concept. Sponges are sessile, meaning they are permanently attached to the seafloor and cannot hunt for food. Because they lack mouths, stomachs, or lungs like other animals do, they rely entirely on a fascinating biological plumbing network called the canal system. By constantly pumping massive volumes of ocean water through their bodies, they filter out tiny microscopic plankton for food, absorb life-saving oxygen, and efficiently flush away toxic waste. This system is the absolute lifeline of the sponge, acting simultaneously as its respiratory, digestive, excretory, and reproductive system. Now that we understand why this system is vital, let us look at its basic anatomy. In zoological terms, this is known as the aquiferous system. It begins with thousands of microscopic in-current pores on the outer surface called ostia. Ocean water enters through these tiny windows and flows into various canals and central cavities, such as the spongiocele. After the water has been thoroughly filtered for nutrients and oxygen, it must leave the body. It exits through one or more large excurrent openings, known as the osculum, which acts like a giant chimney. Moving deeper into the anatomy, we must ask, what actually pumps the water? Since sponges do not have a heart or muscles, the entire flow of water is driven by specialized flagellated cells called choanocytes, or collar cells. These microscopic cells line the internal chambers of the sponge. They constantly beat their whip-like tails to create a steady, unidirectional water current. It is the combined, synchronized effort of millions of these tiny choanocytes that pulls water in through the ostia and pushes it out through the osculum, keeping the sponge alive. Building on the cellular mechanics, it is important to note that the overall architecture varies among species. The complexity of the canal system is generally categorized into three evolutionary grades: asconoid, cycanoid, and leuconoid. The asconoid grade is the simplest, resembling a basic tube. The cycanoid grade features folded internal walls, and the leuconoid grade is the most complex, utilizing highly branched canal networks. Each evolutionary step represents a massive increase in internal surface area. This increased surface area directly translates to higher filtering efficiency, allowing larger sponges to process more water. Before we dive into the mathematics, let us consider the real-world impact of this system. Because sponges process such massive volumes of water to extract enough microscopic plankton to survive, they act as the ultimate water purifiers of the marine ecosystem. The massive pumping action of millions of sponges plays a crucial role in cleaning ocean water and recycling nutrients, especially in coral reef ecosystems. Furthermore, scientists actively study these highly efficient biological filters to understand fluid dynamics in microenvironments and to design better artificial water purification systems for human use. To truly appreciate how the sponge optimizes this ecological role, we must look at the physics of water flow. The sponge faces a unique challenge. It needs water to move very slowly past its feeding cells to catch food, but it needs wastewater to shoot out very fast so it doesn't refilter dirty water. We model this using the principle of continuity for incompressible fluids. The formula is A in times V in equals A out times V out. Here, A in is the total combined area of all tiny entry pores, and V in is the slow entry velocity. On the other side, A out is the area of the large exit hole, and V out is the exit velocity. If the total inlet area increases, the entry velocity decreases, maintaining a perfect balance. Now that we have our continuity formula, let us apply it to a real-world scenario with a large leuconoid sponge. We are given that the millions of tiny entry pores have a massive combined area of 0.5 square meters, and water enters at a very slow velocity of 0.002 meters per second. The single exit opening has an area of 0.01 square meters. We need to find the exit velocity. By rearranging our formula, we divide the total inlet flow rate by the exit area. Plugging in our numbers, we multiply 0.5 by 0.002, then divide by 0.01. The final answer is 0.1 meters per second. This means the water shoots out 50 times faster than it entered. Following our successful calculation, let us look at the mathematical proof behind why this biological design is so brilliant. We start with the continuity equation and isolate the exit velocity. By grouping the area terms, we see that the exit velocity is equal to the ratio of the inlet area to the exit area multiplied by the inlet velocity. Because the combined area of millions of microscopic pores is vastly larger than the area of the single exit hole, this ratio is a very large number. Mathematically, this proves that the exit velocity must be significantly higher than the entry velocity. The sponge has evolved to use simple algebra to create a slow feeding current and a powerful, fast exhaust jet. Having proven how the exhaust jet works, we now turn to measuring the total amount of work a sponge does over time. To do this, we need two new formulas. First, we calculate the volumetric flow rate, denoted by Q. This is equal to the exit area times the exit velocity. Q tells us exactly how much physical space the moving water occupies every single second. Once we have the flow rate, we can find the total volume pumped, denoted by V. We simply multiply the flow rate Q by the total time elapsed, T. If time increases, the total volume processed increases proportionally. These equations allow us to scale up a microscopic cellular effort into a macroscopic environmental impact. Let us put these new formulas to work with a concrete example. We are looking at a small cycanoid sponge with an exit radius of 0.002 meters, an exit velocity of 0.05 meters per second, and we want to find the total volume pumped in one full day, which is 86,400 seconds. First, we calculate the cross-sectional area of the circular exit hole using pi r squared, giving us a tiny area of 0.0000125 square meters. Next, we multiply this area by the velocity to find our flow rate Q. Finally, we multiply this per second flow rate by the total seconds in a day. The final answer is 0.054 cubic meters, which is exactly 54 liters of water. Now that we have calculated the massive volumes involved, let us visualize this entire process. On screen is a cross-section of a sponge. Notice the small blue arrows on the outer edges? These represent ocean water, slowly entering through the microscopic ostia. This slow pace gives the choanocyte chambers, located in the folded walls, plenty of time to filter out food particles. As the water moves toward the center, it converges. Look at the top of the diagram. The large red arrows shooting out of the osculum represent the high-speed exhaust jet we just proved mathematically. This diagram perfectly captures how the sponge balances a slow internal flow with a rapid waste disposal system. We have reached the end of our journey, so let us summarize the key takeaways. First, the canal system is the defining anatomical feature of sponges, acting as a multi-purpose engine for feeding, breathing, and waste removal. Second, this entire system is powered by millions of microscopic choanocytes that create a continuous, life-sustaining current. Third, by applying the principles of fluid dynamics, the sponge perfectly engineers a slow internal flow for efficient food capture and a rapid exhaust jet to expel waste safely. You have now seen how seemingly simple organisms use complex physics to survive and act as the ultimate water purifiers of the ocean. Great job mastering this topic.